Gauss's law can seem pretty complex, but we're going to try to set up some ideal scenarios that are going to simplify things down to make things just understandable enough so that we can make some simple calculations and use it in our math. So we're going to try to define flux as this symbol here that would be, hey, it looks like a Gaussian sphere, and this is going to be my little symbol for flux, because as we can see, it looks exactly like the flux symbol, and this is the electric field that is springing out from this Gaussian surface. That's probably why the symbol for flux looks like that. And we're going to set this equal to the integral of the electric field times dA here, across the area, essentially is what that's doing, dA. And then this is going to be equal to the Q enclosed divided by epsilon naught. Of course, we're supposed to be Newton meters squared divided by coulombs. Okay, great. So this is the official definition of flux, but makes very little sense to me. So what we're going to say is, instead, we're going to say E times A, and then times the cosine of theta, oops, not phi, but theta rather, cosine of theta is going to be equal to the total enclosed charge divided by E naught. Now that might make a little bit more sense, because we're going to try to set up some situations where, in our cases, the cosine of theta is just going to be either 0 or a 90, so that's just going to go away, and it's either going to be 0 or 1, so that will cancel that out. If there's any kind of like degrees here that this thing is not in the perfect position, then it'll make the math really complicated, so we're going to sort of skip all that. This is just an introduction, right? And so the ideal situation is when you have a Gaussian sphere like that, and the arrows of the electric field are just pointing straight out like that. And I'm going to say that this A here is the area of the Gaussian surface that we're going to use, the Gaussian area, because we don't want to get that confused with the area of whatever shape, whatever charge. There might be a conductor with a shape in there we're calculating. This is the Gaussian area, an imaginary area that we're drawing, imaginary circles that we're going to draw everywhere. Now I've drawn a couple of planes here to represent the surface of whatever Gaussian area that we're trying to calculate. So this is going to be the new Gaussian area here. We're just going to make an imaginary area here. And we're going to calculate, okay, so what's the angle between those two? Well, in this case, it's 0. Cosine of 0 is going to be 1. So in this situation, this is 0 degrees right here. And the equation for flux is going to simplify down to E times A. All right, and that's basically that. And on this side, notice how the E is going this way, and it is going to be 90 degrees to the area. So in this case, the flux is going to be equal to 0, because the cosine of 90 is 0. And so the most important thing that we need to do is try to identify which way E is going. Which way is E? This is the big question we need. Which way is E? Answer that question, and then you should be able to figure out what's going on with flux and charges and stuff like that. I'm sure you remember the basics, where we would have the pluses and the minuses, where the arrows are pointing away from the pluses and towards the minuses. But we might also see something like this, where it's coming out of the page, or something like this, where it's going into the page. And these are some of the basic directions that E could be going. But again, the direction of E is really important, because, well, it might be 90, so we'll get 0, or it might be 0 degrees compared to the area normal, so we might get 1, so we could use the equation EA. Or if it's some other angle, then obviously that area, the Gaussian area that we're drawing, is probably not going to be very easy to calculate. In an ideal situation, we're going to be working with conductors, and conductors are always going to be wanting to go towards equilibrium, and so therefore the electric field inside the conductors are always going to be equal to 0, and that's going to make things perfect for us. But let's say we're working with non-conducting insulators. So this is a little bit more difficult, but if we work with the Q being equal to 0 within the insulator, then that's great. Then the electrical field also can be equal to 0. That's going to make things really easy for us. If they have a uniform surface density, then that means that the electrical field is also going to be uniform, and so that's going to be easy. And in this case, we can use Q equals, PV, stuff like that. Or the surface version. Regardless, if we have a non-uniform density, then of course the electrical field is going to be non-uniform, and in that case this is going to be much more difficult, so we want to try to kind of avoid those kinds of calculations. Let's take a look at an example of a conductor. In this case, the electric field is going to be equal to 0 within this region. That's pretty important to know. Now let's say we had a charge inside here of +2. Let's try to draw some Gaussian areas in 3 different locations and see what happens. Let's draw a Gaussian area there. We'll draw one somewhere in the interior region here, somewhere out here, and we'll give them G1, a G2, and a G3 as terms of their radiuses. Okay. Now, if we know that we have a positive charge out here, and I said to you, okay, let's look big picture, and on the outside we're going to draw a sphere here, and all of a sudden, wait a minute, for some reason, we got a +7 charge on the outside. And we're asking ourselves, wait, what? We have a +2 in here, we have a +7 out there. What happened? Well, I'm going to point out a little interesting little formula over here. I'm going to draw very similar to what we have right now, a little shell, and here's my charge inside the shell, here's my charge outside, and I'm going to ask myself, okay, well, what happened? What's the charge of the shell? It's actually just going to be out minus in, and that will give me the charge that the shell actually had. So this shell, if I go 7 minus 2, the shell is actually +5 charge. So that's what we can gather from this little bit of information at first. Now there's going to be charges inside this conductor already, and this +2 is going to attract negative charges from the conductor. They're going to actually line up on the surface here. It's going to be a charge of -2 on the surface of that. But we know that you're supposed to have a net 5 in total. So how do you get from -2 to 5? You have to add 7. Okay, so that's what's actually going to be lining the outside over here, so all the positives are going to be repelled by that, and so they're going to line this outer surface, but it's going to be +7 on the outer surface, and that's how we got the reading of +7 out here, because that is the total of all the charges inside. +2 minus 2 plus 7 equals 7, and because but we have a net charge of only 5 on the conductor, but that's because we have a 5 plus the 2 in the middle, and that's going to give us 7. So let's try to calculate the electric field at each one of these points that we drew on the Gaussian spheres. In the example 1, E1, that's just going to be, we could use Gauss's law for that because we have nothing in there. It's just going to be a small little red circle. It's going to look like that. And the only thing we have inside is the charge enclosed, which is 2, and then we're going to divide that by the that thing, and then we're going to move the area over, so it's going to be on that side, because we're calculating for the electric field. So we've got +2 on top, and then on the bottom we're just going to be dividing by the area of this Gaussian area. What's the Gaussian area? 4 pi r squared. What's r? G1. So we're going to use that. So we have 4 pi G1 squared. And then this is going to be times epsilon naught. It turns out that this equation is just going to be simplified into kq divided by r squared. Great. So that's for E1, simple one. Now for E2, in this case, we're going to be drawing the circle inside here. We know that this is 0 because the electric field in the conductor is equal to 0, so that's fine. All right, but how is it equal to 0? Well, that's because we have the +2 and we have the -2 that's on that side. +2 minus 2, of course, that's going to be equal to 0. We divide that by the Gaussian area. Again, it's going to be 4 pi G2 squared. And this is going to be epsilon naught here on this side. But we can see how this is equal to 0. +2 minus 2. And now in the third example, E3, Here, we've drawn the circle, the Gaussian area outside. Keep in mind, these are imaginary areas, okay? Which is the imaginary circles everywhere. But out here, it's going to be the third one. And out here, we have everything that's enclosed. It's the total sum of all the enclosed charge. It's going to be 7 plus 2 minus 2. So plus 2, minus 2, and then plus 7. Okay, so then in total, essentially, you're just going to get 5 in total, of course, right? But, or no, you get 7 in total, because plus 2 minus 2 is 0, plus 7, you get the 7 total charge. That's how we got all that stuff right there. But regardless, you have the same stuff on the bottom. It's going to be 4 pi G3 squared and epsilon naught, which is going to be equal to K, and then the sum of all the Q's divided by R squared. And that's going to be the third electric field that we have there. So it's actually pretty easy to calculate stuff in the conductor. It's not too bad. Now here's the interesting thing about these conductors is this plus 2 charge, it could be anywhere in here. It doesn't really matter. It's not really going to affect, the distribution of these charges too much. It's still going to be minus 2. It's still going to be plus 7 on the outside. So it's all going to equal out and balance because it's a conductor. Things are going to be easy to move. So this plus 2, it can be anywhere in there. It doesn't matter. It can be anywhere. In fact, we could also have a minus 2 on the inside, and let's consider that scenario too. So it could be a minus or a plus on the inside of this, and of course this is true for any of these situations, but we're just going to look at the minus side for right now. Of course, on the lining of this side, you get the plus 2 again, right? Because now that cancels out and that cancels out. Remember that we have a net of plus 5 on this shell. So how do we get the plus 5? We have to add 5 over here, or add 3 to this side. So we actually have plus 3 on this side, and then all the pluses are going to arrange themselves on the outside as well. We actually have pluses on this side, pluses on that side, but that's because this is a plus 5 total charge. And if we took the sum of everything on the outside, it turns out that this one would have a net charge of plus 3 in total if we calculated that. On this side it was 7 because plus 2 minus 2 plus 7 makes it a 7 total charge. And then on this side we had minus 2 plus 3, giving us a plus 3 in total charge, which is just kind of some crazy stuff, but that's basically what happens. So here I've got a couple of non-conducting insulators, and these are going to be perfect insulators. Pretty important. They're perfect, which means they don't accumulate any charge. We're going to start here first with a charge of 0, and the electric field is equal to 0 for this particular insulator. This one is going to have a charge of plus 5, and it's going to be uniform across the entire thing. But they're both non-conducting insulators. So let's say that this one had a plus 2 charge. Well, in both cases, this plus 2 charge is not going to do anything. None of the charges is going to be affecting this inner walls like it was back here in the conductors, okay? So, that's it. Now the thing is, this electric field, though, of this particular insulator is going to be changed now because there's a charge. So it's going to be influenced by that center thing. Let's see, if we drew a Gaussian sphere there, and we started to try to calculate these things, we could say that E1 is going to be equal to, is only going to have that plus 2 charge, and then, of course, we're going to divide that by the area of the Gaussian sphere, which is the 4 pi G1 squared, and then our epsilon naught, just kind of like we did before, because it's the same thing as we had over there. You get the KQ divided by R squared, no problem. So if we were to try to calculate for E2, on the other hand, E2 would be equal to, well, you get 0 from your from whatever piece of this insulator you have, because here you're going to have no charge, it's just 0. But then you're going to add on whatever you get from your inside, which is plus 2, and you can divide that by your 4 pi G2 squared, epsilon naught, and that's going to be equal to, it's the same thing, so it's KQ divided by R squared. Nothing has changed. But as soon as you go to E3, let's check this out. E3, again, we have the entire thing now being equal to 0 here, and then it's plus 2 from the inside. You can divide this by your area again, and this is only going to be 4 pi G3. Great. Nothing too crazy, nothing too interesting. This is all going to be exactly the same regardless. That's why insulators with no charge are pretty easy. Nothing to do. You just use it as a point charge essentially. Pretty good stuff. Well, now let's look at the second insulator over here. We know that this one's supposed to have a uniform charge, so the entire thing is going to have a charge. We could fill in this piece of it just so we can have a better representation. But again, this plus 2 is not going to do anything to the surfaces. But we are going to have to calculate this uniform charge because there's a charge in here. For that, we're going to need the volume. Remember from before we used PV and stuff. But let's see. The volume of a sphere is 4/3 pi r cubed. And if we take the dV, that's supposed to be the integral of 4 pi r squared dr. So, and this is going to be from wherever your radius is from A here. And then this is going to end possibly at B over here. Okay, so keep in mind that the integral is only going to go from the shells, okay, from A to B here, maximum. It could even stop at G depending on how far you were going to integrate, okay? So let's take a look. On E1, it's exactly the same as before. So you start with your plus 2 on top, and then you've got your 4 pi G1 squared with the epsilon naught on the bottom. And so again, you can just kind of use KQ divided by R squared. But for E2, this is when things finally start getting interesting, because remember that the charge is supposed to be equal to PV, and so we're going to start having our P here. We're going to have the integral from, we'll start at our integral from A here. We're going to stop at whatever G2 value we found. So it's going to be this one. Because we're not doing the entire thing, we're just stopping there. And then we're going to throw in the dV, which is supposed to be 4 pi r squared dr. And not only that, but we're also going to include the plus 2 charge. Plus 2. So this is going to be the final thing. And if you want to take the, divide that by the area, you need to use the Gaussian area, which is 4 pi G2 squared. Okay, the same radius that we used there. Very nice. That might actually even cancel out, and you might get some good numbers there. But we're not going to do that. Then in the third situation, E3, that's going to be all the way out here. We're going to have basically the entire thing here. We already know is a total of plus 5, so we don't really need to calculate too much right there. And then we're also going to add in the plus 2 from that one, which means that this is a pretty easy one. Or you could just take the integral from A to B there. But it is important that you go from A to B here in this particular one. Not going to be, so this particular one would be the integral from A to B. Okay, you're not going to go to A to G because it's going to stop there. And then this on the bottom, you're going to have a G. So 4 pi G3 squared. But you're going to integrate from A to B, or you're just going to encapsulate that on top. All right. Of course, you got your E not at the bottom. And this is going to equal to essentially the sum of the Q's inside times the K divided by R squared. It's a little bit more complicated here, so you can't really simplify this unless you already knew the total charge here. But if you had to integrate, then you couldn't really simplify it. But essentially, it's the total Q times K over R squared. This is kind of all the different situations you might encounter in some of these complicated Gaussian examples. I'm going to list a few of the basic E equations that we should remember. Let's say we had a point or a sphere or a shell. The electrical field for these would only be KQ over R squared, and we can kind of skip through some of the math here. If we had a surface of a conductor, we could use the equation E equals density over E naught. That's just on the very surface of a conductor. If we have an infinite sheet, then we would use E equals density over 2 E naught. And if we had a line or a cylinder, then we could say 2k lambda over r. And these are some of the basic E equations. In this final example, we're going to examine what happens when we have a plus sheet here and a minus sheet over here. We're going to be getting, first of all, some arrows pointing in this direction for the E, and also in that direction on that side. And then over here, we're going to get bunches of arrows going across, of course. And then we're going to reach this side, and it's going to have more arrows going this way. And then we're going to have arrows going this way on that side. If we remember something about infinite sheets and having one of them here and another one there, we might even be able to calculate the electric field in there. It could be equal to this thing divided by, well, there'd be 2 of those. So you would actually just get that. Well, that's interesting. But anyway, over here we have this conductor, and we know that if there's a positive charge over there, we're going to get some negatives on this side. That's also going to line the interior here with some pluses. And then on this side, we're going to get some negatives because of those pluses. And then on this side, we're going to get some pluses. So everything's going to equal out. If we were to try drawing Gaussian spheres in there, everything would just be equal 0. We kind of already know how conductors work. But nothing's really going to happen too interesting over there. Over here we have this insulator. Now the interesting thing about the insulators is well, if the Q is equal to 0, then nothing would happen. It would just kind of be stuck there. The electric field would be equal to well, whatever is over here. So that would be fine. So you could use that equation for the electric field. But let's say you had a charge of negative Q, then all of a sudden this thing would be moving in this direction, right? Because it would be attracted by this positive charge and repelled by this. So this whole insulator had a negative Q charge, it would start moving. That's crazy. And if it had a positive charge, then it would also start moving in that direction. But if it was Q equals 0, then it would just be stuck there, and you can kind of also use that thing to calculate the electric field. But if it starts having a positive charge, I don't think you can use that. Now you have to sort of deal with all that. But if it was Q equals 0, same thing over here. If this was net Q equals 0, again, you could kind of just use that thing right there in order to calculate that. So this is kind of the last example. As you can see, Gauss's law is a little bit intense. You can make a lot of different scenarios up, and you have a lot of variables changing, so it's very complicated. But hopefully this was helpful.